Hello, everyone, and welcome to our talk. I'm Tamara Ringas. I'm a Solidity developer, and this is Ryan Wolhuter. He's a software engineer.
Hi everyone, happy to be here.
Our talk is titled Distributing Instruments for the Internet of Musical Things. We gave a similar talk in 2020, and this is the follow-up where we have found new and improved technologies to even better suit the use cases that we're going to outline. Cool, so what are distributed instruments? A distributed system is one whose components are located on separate computers or devices, which are physically separate, sometimes over huge distances. These components communicate through message passing. Distributed systems are great for musicians who want to do networked collaborations or performances that require synchronization and signal passing over variable sized distances. IOMust. Musical things are devices capable of sensing, processing, and exchanging data for musical purposes. The Internet of Musical Things, IOMust, is the ensemble of interfaces, data, and protocols that enable interactions between humans and musical things. There are a few challenges associated with IOMust. Some are, for musical purposes, the latency must be in the order of milliseconds. The synchronization of audio streams produced by devices don't share the same clock. Even if devices initially share the same clock, they need a periodic resynchronization procedure. There are also many different audio and visual file formats. This is just to show that with a distributed instrument, you could have a person making a video in America and musicians all across different continents, and they could all be working together in one collaboration in real time. Cool, I'll just outline a few of the tools that you can use to do this. The first one is MIDI. I'm sure you all know MIDI. It's a technical standard that describes the communication protocol, digital interface, and electrical connectors that connect a wide variety of electronic musical instruments, computers, and related audio devices for playing, editing, and recording music. Along with MIDI, there's something called Open Sound Control, which is a protocol for communication among computers. It can facilitate messages among computers, synthesizers, and other multimedia devices. It is optimized for modern networking technology, and it doesn't only need to be used for musical purposes. Some applications of OSC are mapping non-musical data to sound parameters in sonification, sensor or gesture-based electronic musical instruments, networked music performances, and OSC is an integral part of SuperCollider, where it is used to facilitate communication between the server and the sound engine. Here's a comparison between MIDI and OSC. MIDI's message types are byte encoded and predetermined, whereas OSC is human readable and user defined. The format that MIDI takes is 1-byte integers, only the integers 0 to 127. OSC can take numbers, text, colors, and even MIDI encodings. OSC also has time tagging, which MIDI does not. MIDI's transport mechanism is cable-based transfer, whereas OSC can be done through LAN and the internet over protocols like UDP, TCP, WebSockets, and WebRTC. The number of channels in OSC is unlimited, whereas in MIDI it is limited to 16. And the transfer speed of OSC is far faster with a gigabit than compared to MIDI. So OSC can be understood as a more flexible alternative to MIDI. OSC clears away many of the ideological and hardware constraints inherent to MIDI in favor of an open-ended, user-defined address space model that provides arbitrary parametric control via standard networking hardware. MIDI messages can be encoded into OSC messages, but what is the best way to send OSC messages?
So we spoke before about using OSC over various communication protocols like WebSockets, for example, which we'll mention later. But since 2020, when we had our last talk, we've seen major growth in a new standard that has emerged called WebRTC. So the RTC part stands for real-time communication, and WebRTC in particular is the set of standards that are being implemented by browser vendors and other companies like Google, for example. in order to facilitate real-time communication over the web. So WebRTC is a set of open standards for real-time, plug-in, free video, audio, and data communication. So historically, RTC has been very corporate and complex. You would have had proprietary vendors who made RTC-based technology. You would need to pay for it. You need to have licensing. It would usually be developed in-house as well, so it would be unlikely that you'd even have access to it. So integrating RTC technology with existing content platforms and services has been really difficult and time-consuming, and especially so on the web, where there wasn't really a set of fixed standards for doing this yet. So WebRTC is now ubiquitous, especially since the boom in video conferencing that happened as a result of 2020 and onwards. So you have definitely used WebRTC already in many different applications, like in Skype, Facebook, Google Hangouts being an obvious example, which is now Google Meets, which we're actually using it right now. So you'll notice that to use this platform, you didn't need to download or install any kind of plugin or proprietary technology. You're simply accessing it through the browser, and that's because WebRTC, the set of standards, is implemented by all of the major browser vendors like Google, Apple, and Microsoft. So the guiding principle behind the web in general and WebRTC in particular now is that it should be open source, free, standardized, and built into browsers, and more efficient than existing technologies. So you can see that this dream has been realized, and largely it's been spearheaded by the need for video conferencing like we're doing now. But you can imagine that if this sort of thing is possible, then doing the same for audio only and for musical performances is definitely within the realm of possibility as well. So up until the current time with WebRTC available, if you wanted to build something like a video conferencing app like Skype, the original Skype before it was browser-based, you would have had to use C and C++, and you would have needed to work with very complicated APIs and audio codecs, and you really do a lot of work from scratch. So what WebRTC does is it does that work for you. So all of this WebRTC architecture under the hood is still built in C++ and C, and it works in the same way, except what WebRTC, the set of standards, provides to you is a wrapper around all of that. That's available to you through JavaScript that's super easy to use and ubiquitous programming language that lives in every browser. So essentially, it's an API layer that sits on top of WebRTC that allows you to use these powerful platform technologies in a much easier to use way.
And we'll outline some of those ways later.
Yeah.
Cool. The default codec in WebRTC is called Opus. Firstly, what is an audio codec? An audio codec is a device or computer program capable of encoding or decoding a digital data stream. In software, an audio codec is a computer program implementing an algorithm that compresses or decompresses digital audio data according to a given audio file or streaming media audio coding format. The objective of the algorithm is to represent the high-fidelity audio signal with a minimum number of bits while retaining its quality. This can effectively reduce the storage space and the bandwidth required for transmissions of the stored audio file. So it's very important to choose a good audio codec when using something like WebRTC.
Yeah. We should also just mention that, so this is the default audio codec of WebRTC. This is the one that they chose, but you can actually send arbitrary data through a WebRTC connection, which we'll explain shortly. So you could also use OSC if that made more sense for your use case.
Yes, exactly, depending on what you want to send. But if you're sending audio, we would recommend Opus. It's a totally
like an audio stream. Like if you wanted to send a stream audio, like if you wanted to send audio messages or like notes or that sort of thing, it might be easier to use something like OSC.
Yes, definitely. Opus is a totally open, royalty-free, highly versatile audio codec. It is unmatched for interactive speech and music transmission over the internet, but is also intended for storage and streaming applications. It is standardized by the Internet Engineering Task Force. He has a graph showing bitrate versus quality. The green points in the graph are royalty-free and open source. And it's just quite interesting that Opus actually has higher quality than MP3 and AAC.
So in our previous talk, we demoed some really cool and really powerful technology that enables this sort of use case, a distributed instrument. And what we used at the time was what is still considered the best server-based programming language architecture for building real-time applications. So things that have a real-time connection where you will have updates on either client happening instantaneously, well, near instantaneously. And we used OSC as our encoding platform for sending these messages. So that worked well, and especially for a closer together use case, like, so, you know, in the same city or something like that, we were able to get pretty solid results. But when it comes to a global platform, like now, we're not just thinking about like a pandemic situation where your friend is in the house next door and you want to jam with them. We would like this sort of thing to be enabling people to jam across the world whenever they want. And the fundamental limitation that we ran into is the server itself. And the fact that when you've got clients, so like you've got my laptop and Tamara's laptop, and they're connecting via a server, that server is going to now be our limiting factor because the server has to process these requests at a certain rate. And then as well, we have to actually connect to the server. So if the server is in an inconvenient location, like let's say I'm in Cape Town, Tamara's in Joburg, and then our server is in Hungary, right? We now have to do this very inconvenient loop, which is significantly adding to our transport time. So what WebRTC offers us is a way to essentially cut out the middleman and not need to run through a third-party server in order to communicate between two clients. So in this case, using the WebRTC protocol, the connection between the two clients or instruments in this case is completely peer-to-peer. So when I'm sending data to Tamara and she's sending data to me, we aren't going through any intermediary. And that allows us to take the service performance out of the equation entirely. And that now makes the limiting factor only the latency and the connection speed between the clients themselves.
Yeah, exactly.
Which is always strictly better than having a third party, because you would still have the speed of the clients mattering, but then you would also have the speed of the server. So always this will work better in all cases. So latency, as we've mentioned, is definitely the biggest problem standing in the way of distributed instruments. So it would be nice to imagine that we have the speed of light on one hand, and then like the maximum perceivable latency of about 30 milliseconds, which is considered to be the boundary below which the human mind perceives sound as synchronous. But actually, recent research shows that when it comes to actually playing an instrument, musicians are more sensitive and more aware of these things, to the point that something around 13 milliseconds is actually going to be perceptible to the musician, the person who is trying to actually keep in sync, because in that mindset, you're more aware. So that actually cuts our space that we have available in half, unfortunately. So that does make the problem more difficult. But there are solutions to these. So the biggest contributor usually is the network speed, so your up and download, and then also physical distance. So the further away, the more traveling needs to actually happen. But there are more problems as well. So when it comes to actual audio processing, like when we're talking about sound card versus not, the inbuilt sound card of a laptop, for example, does a lot of pre-processing to improve quality, clarity, remove noise, and so on. But doing all of that actually adds even more latency, because we now need to wait for those things to happen. So generally, if we're doing applications like this, you will need to use a sound card that is fast and efficient. And so like that, those are the problems that we're facing. Then some of the ways that people have before already like had some success in making these work better is you can isolate your own sound. So if you're using isolating headphones, then it seems that the human brain is naturally able to compensate for some latency, because if you think about it, that's actually already what people do. Because when you look at any given instrument, the sound actually can't come out of it instantaneously. So there is always some amount of latency. And the fact that humans are able to play music together shows that we are, at least to some extent, able to deal with latency. So so isolating yourself through your own sound that you're hearing through the network can be useful, but that's not always possible. And so the biggest problems really come about with vocalists and drummers, because those are the ones that are the most difficult to isolate, and also the ones that are the linchpins in terms of the rhythm and timekeeping. So it depends on the instrument you play. So if you play an instrument, an electric instrument like bass, for example, then you're lucky, because that's much easier to monitor through headphones and to adapt. And yeah, that's pretty useful. But then, like I said, with drummers, that's much more difficult. So there actually are other completely different and novel solutions to these problems as well. And one that is particularly cool is the Ninjam software. So what Ninjam does is that it actually records and streams synchronized intervals of music between participants. And just as the interval finishes recording, it begins playing on everyone else's client. So when you play through an interval, you're playing along with the previous interval of everybody else. So they're actually introducing latency on purpose, and then letting that be a buffer that allows them to keep things in sync. Yeah, it sounds pretty bizarre, but the people who make the software and people who use it say that over time it actually starts to feel quite natural. And they say that it can actually be more forgiving than a usual jam, because of the way that mistakes propagate. It's actually easier to notice and rectify a mistake because you've got a little bit of a grace period. But for me, at least in my opinion, I think that the improvement of technologies like WebRTC and the improvement of our network infrastructure is really going to be the thing that solves the problem of latency in the end. For example, we're streaming high definition video right now, like it's no problem at all. And 5 years ago, even, this would have been very, very difficult, if not even possible. As the networks and the infrastructure becomes faster and more reliable, it actually means that we don't need as many means of coping with latency just in general. And considering the vast improvements that we've already seen, I honestly don't think it's crazy to imagine that the latency problem will just go away eventually.
So there are quite a few cool applications of WebRTC. The first one we're going to speak about is four hands, which is allows two players in anywhere to play a MIDI instrument together, two MIDI instruments together. So that's why it's called four hands. It's for two pianists, but you can set it to any MIDI sound. There's also Jam RTC, and Mixcloud is bringing out a WebRTC implementations. So now instead of doing your mix for DJs and then uploading it and then your listeners listen, you could actually stream it live, which is really exciting. I'm really looking forward to that one. And then there's one called Video Ninja, which I've used for quite a few network performances between Europe and South Africa, and it even has video, and you really don't notice the latency. We'll show a demo now of Four Hands, a tool by George Liu. He's a music technologist in San Francisco, and this is a MIDI device player. So I have my MIDI keyboard here that I'm going to plug in quickly. And then Ryan's going to play on his keyboard, and we're going to send MIDI messages and play these two instruments. I think I'll be electric bass, and Ryan, you can be a piano. And over here it says it's green, number 3, which means we're both connected in this room, and we can now send messages through the pipeline that connects us.
Yeah, and we can see in the diagnostics there that we're a little bit too high on the round trip milliseconds. but I think that is probably to do with the fact that we're both using Wi-Fi and not wired connections.
Mm.
And also, we are in South Africa, which isn't known for having the fastest internet.
Yeah, and we're
So
also
I can
streaming
imagine,
HD video at the same time.
yeah, at the same time, yeah, actually. So I mean, this is under that threshold that we mentioned. Like the theoretical cap on when we perceive things as synchronous or not, which is supposed to be 30. So we for us, ideal would probably, like they mentioned here, is under 20 milliseconds, but it's at least pretty good. I mean, like
Yeah.
it's close, very close,
Mm.
not miles away.
No. Cool. So I'm gonna play some stuff.
Doesn't do anything to make you be able to play piano when you can't, unfortunately. When will they actually come to us untalented folks? Hey,
Well, you could have a teacher. If you had video and this, you could actually do a remote lesson, perhaps.
yeah, maybe make it easier than ever to lip sync, except in this case, maybe like keyboard sync, and just have someone else who's also connected, who's actually killing it. And I'm just sitting there like, look at me.
That's a fun application. Okay, awesome. Now we'll move on to a code snippet. Ryan will take us through how it actually works, a WebRTC connection.
Yeah. So that means that I should share my screen, my entire screen. Yes. Cool. Can you see the screen?
Yes.
All right, great. Yeah, so forehands, you'll find the public repo in our bibliography, so you can take a look at it over there. The meat and potatoes of the logic lives in this main.js file in the public directory. And so I'll show you, first of all, I would just like to clarify that WebRTC, while the communication that happens is completely peer-to-peer between the two clients or whatever number of clients, we still need server architecture in order to connect the two clients. So in order to facilitate the two clients essentially performing a handshake where they agree to communicate with each other via this platform. So we're going to see here some server related code, but just understand that the servers never see this data. Their purpose is only to facilitate the communication. So we have these ICE servers. So these are essentially different relays that exist. There's a lot of free ones available, like this one from Google. They're also called stun relays. So essentially what these do is they facilitate, they're like you can imagine it like a switchboard, where when you want to get connected to a particular other client, it can be, you will communicate with the server will then communicate with the other clients, and the server will then help you, help the two clients to come to agreement to communicate with each other like that. So that's where the ICE servers come from. You can actually have an arbitrary number of these as well. So that increases the reliability even more. So you'll see here they're talking about a signaling server. So this, and they're using the very well-known library socket.io. So the reason that it's using WebSockets isn't because, so I just want to disambiguate here a little bit. So before, we actually, in our previous talk, we were using WebSockets to send the data. So we were actually sending the data up and down WebSockets. That's not happening anymore. So what we're using the WebSockets here is simply to, in real time, perform this connection where we're saying, hey, I'm here, I've created a connection. We usually talk about it in terms of rooms because you can have a room of people who are going to communicate. And then it will emit these different events when another peer has joined and when it's ready to start sending messages. So you'll see here that the logic is totally based on rooms for these servers, because that's all you're really doing is joining a room, and then we're going to be communicating through the WebRTC protocol instead. So that whole rigmarole is just to set up the connection. And now we get into the part where we're actually doing WebRTC. So you'll see we have a peer connection that represents the two or more peers that are communicating, and between them they also have a data channel. So this data channel is the WebRTC pipe, as you can imagine it, that through which we will actually be sending these messages. And you'll see that the data channel is what we use to play notes on the other computer. So you'll see that coming up now. You don't need to worry too much about the messages though. So you'll see here we are creating a peer connection. And what we do is, so this is a totally browser-based API, which is why we can just call new RTC peer connection. This RTC peer connection class already lives in the browser and it's available to all browsers. And that's how we create our peer connection. We set up the ICE candidate, so you don't need to worry too much about this, but essentially this is going to perform that rigmarole to connect the two clients and say, okay, cool, we're using this particular peer connection, as we mentioned. If you are initiating it, then we do some special logic to have the data channel originate from you, but it will then become a two-way connection after that. So they talk about creating offers because the terminology that WebRTC uses is to say, I'm offering a connection to you, do you accept? And then if you do accept my offer of a connection, then we will be connected and we'll be able to send data up and down the pipe to each other through a totally peer-to-peer connection, hence the name peer connection. So this logic over here is just setting up the data channel and reacting to it being set up. They do a little bit of pinging here just to keep sanity and know that you are in fact connected. This all looks quite hairy, but it's really just a little bit of data wrangling to do various actions when data gets sent up and down. It's essentially just determining, like, is this a MIDI message or not? And if it is, then it's going to play a MIDI. So we can see how the MIDI logic works. And I thought you guys might also find this interesting. A lot of people don't know that we have a MIDI browser API as well. So built into the browser is actually MIDI functions, and we can play MIDI directly in the browser. So you define your notes. They've got quite a few interesting things going on with loop pedals and so on, but that's not really relevant to us. They're using that to set up their various sound parameters. So you see here, Navigator. Navigator is essentially the browser. So if you wanted to go back or forward, for example, you would use Navigator. If you wanted to show a browser notification, you'd also use Navigator. And in this case, it's also the thing that will, when it says, do you give permission for such and such application to use your thing, like a webcam or microphone? In this case, it's requesting MIDI access, and that's how we are then allowed to use the MIDI, the built-in MIDI functionality of the browser. So once we have that, we have now set up MIDI, and we set up a bunch of event listeners that essentially will listen to your key presses, and that's how you're able to press like the different keys on the keyboard and have that make a sound. In this case, these are their different sounds. So they've actually mapped a bunch of different MP3s that make these different sounds as they need them. But you could also just synthesize sound directly in the browser using the Web Audio API. So here's how they do their play MIDI. You can see they have a who parameter here, which is essentially which one of the two peers that are connected are we actually going to play it on. So you can see that's why they say who equals me in that case. And then they will listen to key downs or key ups, and they will play sounds accordingly. So, and then this is essentially to do the same thing except playing samplers. So yeah, this is not necessarily relevant, although if you're interested in playing samples in the browser, definitely check out tone.js, very cool library for doing that with. I just want to show you the last little bit of logic. Yeah, so here's how they deal with key downs and key ups. They get the notes that we pass in, and then it triggers the sample on the sampler that we set up earlier. So you can see here they're taking a look, is it coming from them or me or my loop, and playing it. This is just basic, like some getter functions to get the notes. This is the logic to actually map keys, the key downs to the MIDI codes that you want to play. And they play the MIDI function like that. And then if the peer is connected, then they will use this data channel that I mentioned earlier. So this is the data channel that represents the pipe between the two peers. And it has a method on it called send, which lets either of the peers send data up or down the pipe. And in this case, they're sending the MIDI info. And then when this MIDI info is received on the other side, then it will react to it accordingly. And so as far as this app is concerned, because this is the same code that's running on either side of the two peers, so the same code on either browser, it doesn't matter to the rest of the logic whether this MIDI info came from me or from you, it will react to it the same. So when I play a note, it plays a note, and when you play a note, it plays a note as well on both of our machines. And yeah, so this is how it is actually able to react to the MIDI messages. It will play the MIDI when a MIDI message is sent through. It's also able to loop. And the pedal logic is just nice to have additional MIDI stuff. They're able to loop, as you saw, and then this stuff is just for doing their cool little visualization that they do as well. It shows a nice little waveform, but that's not really relevant to the to this discussion. So yeah, just to recap, essentially what we do is we will set up a peer connection. So WebRTC is then activated. We will have access to the data channel, which is how we can send data up and down. And we will send a MIDI message down the data channel, and we will react to it accordingly. And when I send the message, it will also play the sound on my machine as well. And because the latency is so low, we can expect that it will happen at the same time on both machines, and we can expect to be able to at least pretty well keep ourselves in sync. Yeah, that's pretty much how it works.
Really interesting and surprisingly simple.
Yeah, it's not difficult to use at all.
Yeah, that's really exciting. So that was the code breakdown. Yeah, and that actually concludes our talk. Thank you for listening. And if
Thanks,
you'd
guys.
like to contact us, here are our email addresses.